In this video, I'm going to introduce you to the mechanical and the material properties of a tissue, namely how that tissue is going to respond to a load. First, let's start with the mechanical properties. To illustrate these points, let's consider the fact that I'm going to stretch two pieces of elastic tubing. One is going to be blue up on the top, and the other one's going to be green down on the bottom. If I apply a tensile force or a tensile load to that tubing, I hope everybody can understand that it's going to stretch. Now I grab a piece of green tubing, and even if I apply the same force to that green tubing, it may stretch a different amount than that blue tubing. That amount of stretch, or that change in its length, is going to be different for the blue tubing compared to the green tubing. That change in length, or any change in dimension for that matter, is what's going to be referred to as a deformation. So a load is going to create a deformation of a particular tissue. Now let's put the deformation on the horizontal axis, and on the vertical axis, let's put that load. Now for illustrative purposes for this example, we said that force A and force B were going to be the same. So if we draw a straight line here across where that force is being applied, then we have to see where the deformation intersects with that force. We put a point right there, and then we draw a straight line that goes from the origin to that point. That straight line, or more specifically the slope of that straight line, represents the stiffness of that material. In this case, the stiffness of material A, or that blue tubing. Since material B, or that green tubing, had a greater deformation than did the blue tubing, again, we have to draw a point that's going to intersect the deformation with the load, put a point there, and then draw a straight line from the origin to that point. The slope of that green line is going to represent the stiffness of material B, or that green tubing. Notice that material A, or the blue tube, has a stiffer slope than material B, or the green tubing. The steeper slope means that that blue tubing is going to be stiffer than the green tubing. Said another way, the green tubing is going to be more compliant than the blue tubing. Stiffness is going to represent a resistance to change in an object's dimensions. So the stiffer the material, the greater its resistance to change, and the steeper the slope. Finally, we can look at the area that would be underneath one of those curves. The area underneath that curve is going to represent the amount of energy that was being absorbed by that particular tissue. With those fundamentals out of the way, let's take a look at the mechanical properties of strength, deformation, stiffness, and toughness. And we are going to do this by looking at a typical force deformation curve. Again, we're going to plot the deformation on the horizontal axis and the force on the vertical axis. On the far left, you'll notice that we have a very ununiform region of the force deformation curve that is referred to as the toe region. This is the region where the slack is being taken out of the material. The forces are low and the deformations are unpredictable, but to be quite honest, not a lot of exciting things really happen in the toe regions of the force deformation curve. Beyond the toe region, you'll note that we have a fairly linear relationship between force and deformation up to a point that's referred to as the yield point. This is known as the elastic region. The slope in the elastic region is the stiffness of that particular material. It's also important to note that if we are to the left of the yield point, when we unload the material, that material will return back to its original dimensions. Beyond the yield point, we get into the plastic region. In the plastic region, we are going to see that the material is going to start to break apart. And the material will break apart slowly and break apart and break apart and break apart until finally, at the far end of the curve, the force drops to zero because that material is no longer in one cohesive piece. To the right of that yield point is known as the plastic region. And it's important to note that if we were to unload a material in the plastic region, that it's never going to return back to the original dimension it was prior to being loaded. It has what is referred to as a plastic deformation. The area under the force deformation curve is the strain energy. That is how much energy that material can absorb. How much energy a material can absorb is referred to as the material's toughness. Now, when we talk about the strength of a material, that is somewhat of a controversial topic. Some people will suggest because the material starts to break apart, at least at a microscopic level, once we reach the yield point, that the yield point should represent the strength of the material. Other folks will argue that the highest point on that force deformation curve is the largest amount of force that that material can withstand, and that should be referred to as the strength of the material. To kind of sidestep that controversy, I'm going to refer to the peak region of that force deformation curve as the ultimate strength of the material. So again, we can look at the tow region, the elastic region, and the plastic region, and from that we can infer how serious an injury might be. Any injuries that occur in the elastic region may hurt, but they're not going to cause any damage. And I can certainly hurt you without damaging you. That's also sometimes referred to as a first-degree injury. When we get into the plastic region, the material is going to start to break apart. If the material starts to break apart, that's going to be referred to as a second-degree injury. Here we're going to have some damage to the material. And then finally, if we get to the point where the material just breaks apart, that would be referred to as a third-degree injury. So that's how we can use the load deformation curve to relate to the severity of an injury. It's also important to note that the strength, the stiffness, and the toughness are not necessarily all directly correlated with each other. For example, on the far left, you're going to see an example of a material that's going to have high strength, but it's going to be very stiff. And therefore, it's also not going to have a lot of toughness. The green curve, on the other hand, represents a material that has a low strength because the forces or the loads that it can withstand are fairly low, but it's going to have a relatively high compliance, or put another way, a fairly low stiffness. And it's going to have moderate toughness because you see there's a moderate there area under the load deformation curve. Finally, the red material would represent something that has only moderate strength and moderate stiffness, and yet high toughness, because it has a fairly large area under the curve. So again, do not equate high strength with high stiffness and high toughness. They're somewhat not related to each other. Now let's move on and let's talk about a tissue's material properties. When we look at material properties, the first one we're going to look at is stress. Now, I can apply a relatively large force that might not cause any damage, and I can apply a relatively lower force that may cause damage. Why is that? Because we have to consider not only the magnitude of the force, but the area over which that force is distributed. And that relationship between the force and the area over which it's distributed is known as stress. So if I apply a force over a fairly large area, I'm going to have relatively low stress. If I apply that same force over a smaller contact area, then I'm going to have larger stress. So we can see that stress is going to be equal to the force divided by the area. So if I increase the force, I'm going to increase the stress. If I decrease the area, I will also increase the stress since that area is in the denominator. Next, let's talk about strain. And when we're talking about strain, it's important to understand that when an object deforms, we have really no idea the consequences of that deformation. And what I mean by that is, let's say a material deforms by 2 centimeters. Let's say we stretch it 2 centimeters. Is that a lot or is that a little? And the truth is, I have absolutely no idea because I don't know what the original length of that material was. If that material was originally 2 centimeters long and we stretched it by another 2 centimeters, that would be quite substantial. If we stretched a 2-meter material by 2 centimeters, it's not going to be quite so dramatic. So again, what we have to look at is we have to look at what was the original dimension of that material and then how much that material actually changed in terms of its dimension. So the deformation we said was the change in dimension. The strain is going to be the change in dimension divided by the original dimension. And then we usually multiply that by 100 and express it as a percentage. Say 50% strain, 10% strain, 100% strain. You get the idea. Now, we can go ahead and we can plot a stress strain curve, much like what we plotted for a load deformation curve. And when we plot a stress strain curve, the slope in that elastic region of the stress strain curve is going to be what's referred to as the elastic modulus or Young's modulus. And again, that's going to be the change in stress divided by the change in strain, or the slope on that stress strain curve. Similar to what we did with the load deformation curve, we can divide the stress strain curve up into its tow region, its elastic region, and its plastic region. And the consequences of loading that material into those different regions will be interpreted very similarly to how they were for the load deformation curve. Finally, we can say the area under the stress strain curve is the strain energy density. It's not the strain energy, that's the area under the load deformation curve. But how dense that energy is in a particular area, if you will, is going to be your strain energy density, or the area under the stress strain curve. So those are your mechanical and your material properties. I'm going to ask you in class why it is that we have, or why we look at both the mechanical as well as the material properties. Why not just look at one or the other? Why must we consider both the mechanical and the material properties of a particular tissue? And I think that will make a great discussion for class.